Orcas have torn apart great white sharks, they have killed blue whales, they have hunted in coordinated packs and left the ocean's most feared creatures with no defense. There is almost nothing in the sea they cannot take down. Deep beneath the Arctic ice, a shark the size of a pickup truck has been swimming for 400 years. Orcas share its ocean. They cross its territory and they leave it completely alone. We are going to find out why. We will go into the abyss, into the poison, into the frozen dark where the rules change completely. If you enjoy this journey, drop a like and subscribe. Let's go. Somewhere in the North Pacific, a great white shark is swimming alone. It is 12 feet long. It weighs over 1,000 pounds. It has spent years becoming one of the most feared animals on the planet. Its teeth can cut through bone. Its senses can detect a single drop of blood from 3 miles away. Every other creature in its range gives it space. Then the orcas arrive. There are 6 of them. They move in formation, silent and deliberate, like a team that has run this play 100 times before. The great white tries to turn. One orca cuts off the escape route. Another comes from below. In under 2 minutes, it is over. The shark is flipped upside down, locked in a paralyzed trance, and the orcas take exactly what they came for. The liver. Clean, efficient, total. Orcas do this across every ocean on Earth. In the Gulf of California, scientists watched a pod coordinate an attack on a whale shark, the largest fish alive, stretching 40 feet and weighing more than a school bus. The orcas rammed it at full speed, working in shifts, until the animal could no longer move. They took the liver and left the rest. In the waters off South Africa, 2 orcas named Port and Starboard became so specialized at killing great whites that their arrival alone caused every great white shark in the region to flee the area for months. Just 2 animals. Entire populations of apex predators running from them. Scientists have documented orcas hunting sperm whales, humpback whales, walruses, sea lions, dolphins, rays, and at least 37 distinct species of marine mammals. Offshore orca populations in the Pacific have made Pacific sleeper sharks a regular part of their diet. These are deep, cold water sharks that most predators never touch. The pattern is clear. If it lives in the ocean, orcas have probably figured out how to kill it. They learn. That is the terrifying part. Orca pods pass hunting techniques down through generations like a family recipe. A matriarch teaches her offspring. Those offspring teach theirs. The knowledge compounds over decades. Specific pods develop specific skills, and those skills get sharper every generation. This is why what comes next is so hard to explain. There is a shark in the Arctic Ocean right now. It is 24 feet long. It weighs close to 2,000 pounds, roughly the same as a full-grown horse. It moves through the same freezing waters where orca pods hunt. It has been doing this for centuries, possibly 4 centuries. And in all that time, across all that documented orca hunting history, spanning every ocean and dozens of prey species, this shark has never once appeared in the confirmed diet of a wild killer whale. Scientists have studied what orcas eat in the North Atlantic. They have catalogued seal remains, fish bones, whale tissue. The Greenland shark shows up nowhere. That absence is loud. Every other dangerous or difficult animal eventually ends up on the orca menu. But this one ancient, slow, enormous shark keeps swimming. Every single day. And the orcas leave it alone. The answer involves poison. It involves darkness. It involves depths so extreme that even the ocean's greatest hunters cannot follow. And it starts with a wall that killer whales physically cannot cross. Picture the ocean as a building with dozens of floors. Orcas live on the top 3 floors. The sunlit zone, the first 600 feet, is their world. This is where they hunt. This is where they breathe. This is where their entire social structure operates. They can push down to deeper floors occasionally, but it costs them enormously in energy and time. Their lungs run out. The pressure builds. The darkness closes in. For an air-breathing mammal built for speed at the surface, going deep is like running a sprint while holding your breath. The Greenland shark does not live on the top floors at all. It lives in the basement. During summer months, these sharks cruise at depths between 600 and 2,400 feet below the surface. When they want to disappear completely, they drop even further, reaching almost 4,000 feet down. To put that in perspective, the Empire State Building stands about 1,400 feet tall. The Greenland shark can descend to depths nearly 3 Empire State Buildings stacked on top of each other and still keep going. At 4,000 feet, no sunlight reaches. 0, the water is near freezing, hovering just above the temperature where salt water turns to ice. The pressure at that depth would crush an unprotected human being in seconds. Sound behaves differently down there. Vision becomes useless. It is a completely different world operating by completely different rules. And the Greenland shark is perfectly at home. Its body is built for that environment in ways that took millions of years to develop. Its tissues are dense and cold. Its metabolism runs so slow it barely registers. Where a tuna or a dolphin burns through energy at a furious rate just to stay warm and mobile, the Greenland shark conserves everything. It is not in a hurry. It has never been in a hurry. It has a body plan designed for the long, cold, patient game of surviving where almost nothing else can. Scientists first started tracking how deep these sharks go using satellite tags attached to their fins. What came back surprised the research teams. The tag showed the sharks descending far beyond what most deep-sea fish reach. And they stayed down there. For hours. For days. Moving slowly through total darkness with no apparent urgency. Here is where the story gets stranger. The Greenland shark does not stay in the deep purely out of preference. The depth is protection. Staying below the range where orcas operate means staying below the range of the most dangerous predator on the planet. Whether the shark evolved this behavior as a direct response to predation pressure or simply stumbled into a survival advantage over millions of years, the result is the same. The deep water is a shield, and the orcas cannot reach it. But depth alone does not fully explain the story. Even in winter, when cold surface temperatures pull the Greenland shark upward toward shallower water, the orcas still leave it alone. There is something else protecting it. Something inside the shark itself. Something that makes eating one a catastrophic mistake for any predator bold enough to try. The shark carries a weapon in its own flesh. And it did not choose it. Evolution built it in. The Greenland shark is toxic. Every part of it, the muscle, the organs, the skin, all of it carries a chemical that turns into a neurotoxin once another animal digests it. This is not venom the shark injects. This is a substance woven into its body at the cellular level, present in every bite of its flesh, impossible to avoid without very specific preparation. The chemical is called trimethylamine oxide. Scientists use that name in research papers. For this story, think of it simply as the antifreeze compound. Here is why the shark has it. Water at 4,000 feet deep does not just feel cold. It actively attacks biological tissue. Proteins inside living cells are built to function within a certain temperature range. Drop too far below that range and the proteins start to warp and fail. Ice crystals form inside cells and destroy them from within. Most animals cannot survive these conditions for more than minutes. The Greenland shark floods its tissues with the antifreeze compound to counteract this. The chemical wraps around the shark's proteins and holds them stable even at temperatures that would shred the internal machinery of almost any other animal. It works perfectly. The shark thrives in water that would kill most other creatures almost instantly. The problem appears when another animal tries to eat the shark. Once the antifreeze compound enters a warm digestive system, it breaks down. The breakdown product is trimethylamine, and trimethylamine is a powerful neurological disruptor. It crosses into the bloodstream, travels to the brain, and starts interfering with the signals that control movement and coordination. An animal that eats raw Greenland shark meat begins losing control of its own body. The symptoms look like extreme drunkenness, staggering, loss of balance, disorientation, inability to move normally. For a predator in the ocean, that is fatal. A killer whale that ingested enough Greenland shark flesh would be incapacitated. An incapacitated orca cannot surface to breathe. An orca that cannot surface drowns. The poison does not need to be lethal in a direct sense. It just needs to make the predator vulnerable long enough for the ocean to finish the job. Dogs experience this same effect when fed raw Greenland shark meat on land. They show clear signs of severe neurological distress within a short period. Sled dogs in Greenland and Iceland were historically never fed this shark raw for exactly this reason. Fishermen learned through generations of painful experience that the meat required very specific treatment before any animal could safely eat it. What makes this especially strange is that the shark is essentially poisonous by accident. The antifreeze compound is a survival tool built for cold water, not for defense. The toxicity toward predators is a side effect, but it works so well that it functions like an armor the shark wears invisibly, one that costs it nothing and protects it from almost every animal capable of biting through its skin. There is something even more striking here. The shark cannot remove this chemical, it cannot turn it off, it cannot store it somewhere safe. The antifreeze compound exists in every cell of its body because every cell of its body needs it to survive. The shark is the poison. And that changes everything about how any predator has to approach it. Including, as we will see next, the hunters who are usually smart enough to find a way around any obstacle. Word spreads in Iceland the hard way. A fisherman pulls a Greenland shark onto the dock. It is enormous, strange-looking and unfamiliar to the crew. Someone decides to try the meat. It gets cooked or eaten raw, accounts differ, and within hours the people who consumed it begin to feel deeply, disturbingly wrong. Their coordination fails. Their vision blurs. Their bodies feel like they belong to someone else. The experience is described consistently as extreme drunkenness without any of the pleasure. For dogs fed the raw meat, the reaction is faster and more severe. Sled dogs in Greenland and Iceland were among the first animals observed suffering from Greenland shark toxicity. The animals that pulled sleds across frozen terrain for survival, dogs bred for endurance and cold tolerance, were knocked flat by a few bites of raw shark flesh. Their handlers quickly established a strict rule: never feed this shark to the dogs without treating it first. That treatment became a cultural institution. The Icelandic method of preparing the shark is called fermentation. Fishermen gut the shark, remove the worst of the toxic fluids, then bury the carcass in gravel or coarse sand near the shoreline. The weight of the gravel presses liquid out of the flesh over several weeks. Then the shark is hung in open air to dry for several months more. The full process can take close to 6 months. During that time, the antifreeze compound slowly breaks down and drains away. The resulting product, called hakal, still smells intensely of ammonia, strong enough to make first-time visitors step back immediately. But the neurotoxin is gone. The meat becomes safe to eat, even if most people find the smell alone difficult to handle. This tells us something important about the toxin. It is not a fixed, permanent poison in the way that cyanide or arsenic is fixed. Given time, exposure to air, and physical pressure, the compound degrades. But that process takes months and requires very specific conditions. In the ocean, where a predator would swallow the meat whole and digest it within hours, none of those conditions exist. The toxin stays active. The digestive system breaks it down into its most dangerous form, trimethylamine, and the animal pays the price. There are no recorded cases of an orca attempting to eat a Greenland shark and surviving to hunt again. The reason scientists believe this is because orcas are highly intelligent, and their feeding behaviour is passed down culturally. If a pod had once attempted to eat one of these sharks and suffered the consequences, That event would almost certainly have reshaped the pod's behaviour permanently. The absence of Greenland shark in orca diets may itself be the record of a lesson learned long ago. An orca poisoned in the open ocean, unable to surface, unable to coordinate movement, would drown quickly. Its pod would observe, the matriarch would remember, and the memory, once encoded into the pod's cultural knowledge, would pass to every generation that followed. The ocean keeps no written records, but orca behaviour keeps something better. It keeps the result. And the result, across every documented orca population in the North Atlantic and Arctic, is the same: leave the Greenland shark alone. But what if the poison was not the only reason? What if there was a deeper layer of protection that even the most intelligent ocean predator could not overcome with knowledge or strategy? Orcas look unstoppable. They swim at speeds up to 4 miles per hour. They coordinate attacks with the precision of a military unit. They communicate with each other in real time using clicks and calls that carry specific information. They have been observed teaching their young, mourning their dead, and playing games with no survival purpose whatsoever. Their brains are among the most complex of any animal ever studied, and yet they have a hard ceiling. Every orca is a mammal. That single biological fact determines everything. Mammals breathe air. Air exists at the surface. The surface is the one place every orca must return to, no matter how deep the hunt takes them, no matter how close they get to a target. When the oxygen runs out, they come up. Every time. No exceptions. The deepest confirmed orca dive on record sits at around 3,000 feet. That sounds impressive, and in most contexts it is. But a 3,000-foot dive is the absolute outer limit for these animals, achieved rarely and at enormous cost. An orca cannot simply patrol at 3,000 feet the way a great white patrols a reef. The dive burns massive energy, the oxygen depletes fast. The animal must turn around and ascend long before it can establish any kind of hunting territory at that depth. The Greenland shark's preferred depth during summer months starts at around 600 feet and commonly reaches 2,400 feet. Its maximum recorded dive touches nearly 4,000 feet. That means the ranges only barely overlap at the very top edge of where the Greenland shark operates, and at that overlap zone, the orca is already burning through its oxygen reserves just to get there. A hunting orca needs time. It needs to locate prey, approach without detection, coordinate with its pod, execute the attack, and complete the kill. All of that takes time. Underwater, time is oxygen, and at the depths where the Greenland shark actually lives, an orca simply runs out of time before the hunt can work. There is also the cold. Orcas in the Arctic are adapted to cold water, among the most cold-tolerant mammal populations on Earth, but they generate heat internally and must work constantly to maintain their body temperature. Extreme depths are also extreme cold. The deeper an orca goes, the faster it loses heat relative to the enormous energy it burns keeping its body running. The Greenland shark generates almost no heat. It runs at the temperature of the water around it. Cold is its default state. It costs the shark nothing. So imagine two animals approaching the same depth. One is burning oxygen at a high rate, losing heat, working against the pressure, knowing it must ascend within minutes to survive. The other is gliding through its natural habitat at a pace slower than a walk, completely unbothered, perfectly matched to the environment. The orca arrives at a disadvantage it cannot train away. The shark holds the advantage simply by existing where it always has. But depth and poison are still only two parts of the story. The third part involves something less obvious and perhaps more fascinating: the orca's own mind and the rules it refuses to break. Orcas are not just intelligent, they are culturally intelligent. That distinction matters enormously. Most animals learn from direct experience. Touch a hot surface, pull back, remember the pain. The lesson lives in one animal. It dies with that animal. Each generation starts from scratch. Orcas do not start from scratch. Knowledge in an orca pod moves between individuals the same way knowledge moves in a human family. A matriarch, typically the oldest female in the group, carries decades of accumulated experience and actively passes it to the younger members of the pod. Which fish swim in which waters during which season, which prey to target and which to avoid, which strategies work against which animals. The information travels through the pod like a living library, updated and refined over generations. Scientists call these distinct groups ecotypes. Each ecotype is essentially a cultural nation. They share a range of ocean but operate by completely separate rules. They eat different things, they use different calls, they have different social structures, and critically, they almost never mix or teach each other. In the North Atlantic and Arctic, the resident orca ecotypes are fish specialists or marine mammal hunters. One group follows herring schools across hundreds of miles, perfecting the carousel feeding technique where they herd the fish into tight balls near the surface, then stun them with tail slaps. Another group hunts seals and small whales, using coordinated beach runs or wave washing to knock prey off ice floes. Neither group hunts deepwater sharks. There is no ancestral knowledge in any Arctic orcapod for how to locate a Greenland shark, pursue it into the abyss, neutralize its toxic flesh, extract the liver, and survive the process. That knowledge never existed in these populations, which means it was never passed down, which means no orca alive in that region knows how to attempt it. And orcas are conservative hunters. They specialize. They do not experiment widely with prey types when their current diet is sustaining the pod. A herring hunting orca in Norway has no evolutionary pressure to experiment with a massive toxic shark that lives at dangerous depths and offers no guaranteed reward. Compare this to the offshore orca populations in the Pacific. These pods have developed a specialization in hunting sharks over generations. They have the coordination, the techniques, the cultural memory of how it works. When scientists tracked them, they found Pacific sleeper sharks showing up regularly in the offshore orca diet. These are large, deep water sharks in the same biological family as the Greenland shark. But Pacific sleeper sharks do not carry the same level of the antifreeze compound. The toxicity is lower. The risk is manageable. The Arctic Greenland shark sits in a different category entirely. The right knowledge does not exist where the Greenland shark lives. The orcas that share its territory never learned to hunt it. And the orcas that know how to hunt sharks are thousands of miles away in a different ocean. Knowledge is power. The absence of knowledge is a wall, but there is one moment each year when the wall almost comes down. One window in time when these two animals come close enough that an encounter seems inevitable, and what happens during that window is stranger than most people expect. Every year the Arctic shifts. Summer turns to autumn. The water at the surface cools, then cools further. The temperature drops toward freezing, and with it, something changes in the Greenland shark's behaviour. The shark begins to rise. The deep, cold sanctuary it occupies through the warmer months becomes less necessary as the surface water reaches temperatures the shark finds comfortable. It moves upward toward shallower zones, hunting near the edges of the ice, sometimes visible in water less than 100 feet deep. On paper, this is the moment the orca could act. The Greenland shark is now within range. The depth barrier narrows. The two animals exist in the same vertical column of water at the same time. For the first time all year, a hunt seems physically possible. But something else is happening at the surface. As the temperature drops, the sea ice returns. Sheets of it push out from the coastline and spread across the Arctic Ocean. The ice thickens. It closes over the surface in expanding patches, covering the water that orcas depend on for every breath they take. For a killer whale, sea ice is a genuine threat. The animals need to surface every few minutes. If ice closes over their escape route while they are hunting below, they can become trapped. Documented cases exist of orcapods caught under thickening ice in the Arctic, unable to find open water in time. The animals that cannot find a breathing hole drown. Orcas know this risk. They respond to it by avoiding dense sea ice during the months when it forms most aggressively. The same cold that brings the Greenland shark upward drives the orcapods out toward open water or toward more southern latitudes. The window opens, then closes. The Greenland shark rises into shallower water just as the orcas retreat from it. The timing is not perfect. There is some overlap. Some region and some years produce situations where both animals are present at similar depths near the ice edge. But the orca's instinct to avoid the ice, combined with the shark's continued toxicity and the low visibility under winter Arctic conditions, keeps the encounter from becoming a hunt. Dark water. Moving ice. A toxic target moving slowly through near-freezing cold. Even if an orca wanted to attempt the hunt, the conditions work against every advantage that makes Orcas effective. They need coordination. Coordination requires communication. Communication requires the pod to track each other's position. Under thick sea ice, in near zero visibility, in water that disrupts their normal sound environment, that coordination breaks down. The shark moves through the darkness unbothered. The ice above it is a ceiling that protects it. The cold around it is a home. The season that should expose it instead shields it behind conditions that neutralize the orca's greatest strengths. The window closes. Winter deepens. The orcas move on. And the Greenland shark descends again, back into the abyss, back into the dark, carrying its 400-year-old body through water where almost nothing else dares to go. It has survived another cycle. Another year. Another near miss with the ocean's most dangerous predator. But how exactly does a shark with almost no speed survive at all? How does it find food? How does it avoid becoming prey to anything? The answer involves a hunting strategy so strange it seems impossible. The Greenland shark moves at less than 1 mile per hour. Take a moment to picture that. A healthy adult walking at a casual pace covers about 3 miles per hour. The Greenland shark covers roughly 1/3 of that. It is, by a significant margin, the slowest shark ever recorded. Its cruising speed is so low that it barely registers as movement on underwater tracking equipment. And yet, it eats seals. Seals are fast, alert, and agile. In the water, a harbour seal can reach speeds of 23 miles per hour. It can change direction instantly, dart through kelp forests, and outmaneuver most predators with ease. By every measure of athletic ability, a seal should be completely untouchable to a shark that cannot exceed 1 mile per hour. So how does this happen? The seals make a mistake. A very specific and very exploitable mistake. Seals sleep in the water. They enter a state of rest at or just below the surface, floating with minimal movement, conserving energy during long periods between active hunting. While sleeping, their reaction time drops to near zero. They do not hear the approach. They do not feel the pressure wave. They do not wake up in time. The Greenland shark generates almost no hydrodynamic noise as it moves. No splashing. No turbulence. No vibrations spreading outward through the water column. Its body is so slow and so cold that it creates almost no disturbance at all. The shark glides toward a sleeping seal the way fog rolls in, present before anything knew it was coming. Scientists examining Greenland shark stomach contents found seals in extraordinary condition. The seals showed no signs of a struggle, no defensive wounds, no evidence of a chase, just a complete capture with what appears to have been total surprise. The shark does not need speed, it needs patience and silence, and it has an unlimited supply of both. This hunting strategy works because the Greenland shark has essentially become invisible to prey that relies on detecting movement and sound. Sitting in pitch-dark water at near freezing temperatures, moving slower than a human stroll, the shark produces almost no signal that any prey animal's sensory system can pick up. The same invisibility that lets it hunt seals also makes it difficult for larger predators to locate it in the first place. Orcas use echolocation to find prey. They emit clicks that travel through the water, bounce off objects, and return with information about the size, shape, distance and movement of whatever is out there. A fast-moving fish produces a clear, strong return signal. A large, fast shark produces an even stronger one. But a slow-moving, cold-bodied shark in deep, cluttered water near the rocky continental slopes where sound bounces unpredictably produces a weak and confusing signal. The orca's most powerful sense becomes less reliable exactly where the Greenland shark lives. Slow, silent, cold, invisible to both prey and predator, the Greenland shark turned its apparent weakness into a survival system so effective it has barely changed in millions of years, and the body running that system is stranger than almost anything else in the ocean. Put your hand on your chest right now. Your heart is probably beating somewhere between 60 and 100 times per minute. At rest, doing nothing, just existing. That steady rhythm is burning energy constantly, pushing warm blood through your entire body, keeping your organs running at full speed. The Greenland shark's heart beats approximately once every 12 seconds. In a full minute, the human heart fires 60 to 100 times. The Greenland shark's heart fires 5 times. 5. The entire circulatory system of this enormous animal is operating at a pace so slow that by comparison, it is barely running at all. This is not a defect. This is engineering. The frigid water of the deep Arctic pulls heat away from living tissue constantly. Any animal generating significant body heat in that environment burns through energy reserves at a catastrophic rate. Warm-blooded animals like seals and orcas must eat enormous amounts of food just to maintain their core temperature. They are in a constant race between heat loss and calorie intake. The Greenland shark opted out of that race entirely. Its body runs cold, matching the temperature of the water around it. Its heart beats slow, circulating blood at the absolute minimum rate needed to keep the animal alive. Its muscles move at a fraction of the speed of any comparable predator. The entire organism is tuned for maximum efficiency in minimum energy expenditure. Scientists estimate that a Greenland shark may go weeks between significant meals. Its metabolism is so slow that the energy from a single large seal could sustain it for an extended period that would leave most other large predators starving. The shark is essentially running on the lowest possible setting at all times, and at that setting it can keep running for an almost incomprehensible amount of time. That slow heartbeat is directly connected to something even more extreme about the Greenland shark. The low metabolic rate does not just conserve energy, it slows down every biological process in the shark's body. Cell division, tissue repair, growth, all of it operates in slow motion. The shark grows roughly 1/3 of an inch per year. To reach 24 feet in length, a Greenland shark needs centuries, not decades. Centuries. The animal swimming through the Arctic right now, the one that is 20 feet long and still considered relatively young by the standards of its species, may have been born before the American Revolution, before railroads, before electricity, before telescopes powerful enough to see other galaxies, and it is still alive, still hunting, still gliding through the same cold dark it has always known. But the age question is where this story takes a turn that even the scientists who study these sharks describe as surreal. Because dating the Greenland shark required throwing out every standard method biologists use to age fish, and finding something completely unexpected buried in the centre of the shark's eye. Aging a fish is usually straightforward. Fish produce rings in their bones and scales as they grow, 1 ring per year, the same way trees produce rings in their trunks. Count the rings, get the age. Simple, reliable, used by marine biologists for over a century. The Greenland shark produces no such rings. Its growth is so slow and so steady that no annual pattern forms. The tissues that other fish use as biological calendars remain smooth and unbroken in the Greenland shark. Scientists had no way to determine how old these animals were for a long time. They knew the sharks were old. The size alone suggested it, but the actual number remained out of reach. Then a team of Danish and Greenlandic researchers tried something unusual. The centre of the eye lens in any vertebrate animal is formed during embryonic development, before birth, and it never changes after that. The proteins at the very core of the lens are laid down while the animal is still inside its mother and remain there, intact, for the entire life of the animal. Those proteins are essentially a biological time capsule. By using a technique called radiocarbon dating on the proteins at the centre of the eye lens, the team could measure the ratio of specific carbon atoms trapped inside at the moment of birth. Carbon ratios in the ocean shifted dramatically during the period of nuclear weapons testing in the 1950s and 60s, creating a clear signature in any animal born after that time. Animals born before that period carry a different ratio. The sharks with no nuclear testing signature were old. Very old. The team analysed dozens of Greenland sharks. The largest animals in the group showed carbon ratios consistent with an age between 300 and 500 years, with the best estimate for the oldest individual sitting at around 390 years, with an error range that could push the upper limit past 450. The oldest known vertebrate animal ever recorded. Vertebrates include fish, amphibians, reptiles, birds, and all mammals. Every animal with a backbone. The oldest verified tortoise ever lived to about 190 years. The oldest verified human lived to 122. The oldest Greenland shark in the study blows past all of them. A 400-year-old Greenland shark was alive when Shakespeare was still writing plays. It was alive during the founding of the first permanent English settlement in North America. It was born into an ocean that had never heard the sound of a diesel engine, never felt the turbulence of a propeller, never encountered a fishing net. And it is possibly still out there right now. But an animal that lives 400 years and grows 1/3 of an inch per year raises an immediate question. When that animal is young, when it is small and slow, and not yet large enough to defend itself through sheer mass, what keeps it alive? The parasite on its eye is part of the answer, and it is one of the strangest things attached to any animal on Earth. Most adult Greenland sharks are blind, not partially, functionally blind. Their corneas, the clear outer layer of the eye that allows light to enter, are covered by a pale bioluminescent parasite that attaches itself directly to the surface of the eye and never lets go. The parasite is a small crustacean, roughly the size of a thumbnail. It latches onto the cornea early in the shark's life and feeds on the eye tissue. As it grows, it causes damage and clouding that progressively destroys the shark's ability to see. By the time the shark reaches adulthood, the parasite has been living on its eye for decades, and the shark's vision is essentially gone. In almost any other predator, blindness would be a death sentence. Predators need to locate prey. They need to judge distance and movement. They need spatial awareness to avoid obstacles and navigate terrain. Losing vision removes all of that in most species, leading to starvation within days or weeks. The Greenland shark does not seem to care. Its other senses compensate in ways that remain partially understood by science. The shark's lateral line system, a row of pressure-sensitive cells running along both sides of its body, detects water movement with extraordinary sensitivity. Any animal moving through water nearby creates tiny pressure changes that the shark can feel. The system works in total darkness. It works at extreme depth. It works regardless of whether the shark can see anything at all. The shark also possesses a highly developed sense of smell. The antifreeze compound in its flesh does not affect its olfactory ability. Scientists believe it can detect chemical signals, including the scent of dead or injured animals, from considerable distances even in deep water. Add to this the fact that most of its prey, the sleeping seals, do not move while the shark approaches, and blindness becomes a manageable condition rather than a fatal one. But there is another dimension to the parasite that moves this from strange to genuinely bizarre. The parasite glows. Bioluminescence, the ability of living organisms to produce light, is common in the deep ocean. The parasite attached to the Greenland shark's cornea emits a faint glow in the darkness. The purpose of this glow is still debated among scientists. One possibility is that it attracts small creatures toward the shark's face, essentially luring food within striking distance. Another possibility is that it serves a purpose for the parasite itself, attracting mates or warning competitors. The shark, already blind, cannot see the light its own parasite produces, an ancient, slow, toxic, blind shark cruising through the abyss with a glowing creature attached to each eye, carrying no plan except patience, still managing to survive centuries and grow to 24 feet. What it finds to eat in that darkness goes far beyond sleeping seals. Some of what scientists have pulled from Greenland shark stomachs makes the blindness seem like the least remarkable thing about this animal. A marine biologist in Greenland opens a shark stomach. Inside, intact and unmistakable, is a reindeer. A full reindeer. An animal that spends its life on land, crossing frozen tundra, standing several feet tall at the shoulder. An animal that, by every logical assessment, should have almost no contact with a deep-sea shark living at 4,000 feet below the surface. And yet, this was not an isolated case. Scientists examining the stomach contents of Greenland sharks have found polar bears, they have found horses, they have found moose, they have found entire seals and large fish and seabirds. The variety of prey recovered from Greenland shark stomachs is so wide and so unexpected that it fundamentally changed what researchers thought they understood about how this animal feeds. The large terrestrial animals, the reindeer and the horses and the bears, almost certainly arrived in the shark's stomach as carrion. Animals that drowned in the ocean or fell through thin ice or were washed off coastlines during storms sink to the seafloor and decompose. The Greenland shark, moving slowly through the deep with its highly sensitive nose, detects the chemical trail of decomposing flesh and follows it. The shark is an opportunist of the highest order. Anything edible that enters its range, at any depth, will eventually be found. The polar bear case is worth pausing on. A polar bear is one of the most formidable land predators alive. An adult male can weigh over 1,000 pounds and is an accomplished swimmer capable of covering dozens of miles in open water. Finding bear remains in a Greenland shark stomach raised an obvious question. Did the shark kill the bear, or did it find the bear already dead? The stomach contents did not allow scientists to determine which happened. The tissue was too digested. But the leading explanation is scavenging. A bear that drowned in the Arctic, possibly exhausted after a long swim or lost in a storm, sinking slowly toward the seafloor, would represent an enormous meal for a shark that specializes in patience over pursuit. Whether the shark occasionally takes healthy prey animals that enter the water is still an open question. Some researchers point to the seal capture data, where perfectly healthy seals end up in shark stomachs with no evidence of a struggle, and suggest the shark may be more active a predator than its speed implies. A bear or a reindeer swimming near the surface might be vulnerable to a slow approach from below, particularly in the cloudy dark water near Arctic coastlines. The Greenland shark does not need to be fast. It needs to arrive before anything else does. Its stomach is a record of every opportunity the deep ocean offered, stretching back potentially decades between a single animal's meals. But what is scavenging, and what is active hunting, and what crosses the line between the two? The next chapter goes somewhere even darker, to the question of whether a predator that nobody hunts might itself be hunted by something most people never consider. The Greenland shark avoids orcas. That story is clear. But does something hunt the Greenland shark? On the surface, the combination of extreme depth, slow movement, toxic flesh, and enormous size makes the shark seem essentially invulnerable to predation, and in the documented record, no predator is confirmed to regularly hunt live Greenland sharks. The scientists who study this animal have found no bite marks from known predators, no behavioural evidence of escape responses, no observed attacks in the wild. However, the deep ocean is largely unobserved. What happens at 4,000 feet rarely makes it onto a camera. Sperm whales. The sperm whale is the deepest diving large predator on Earth. A mature adult can reach lengths of 60 feet and weigh up to 90,000 pounds. It dives routinely to depths of 7,000 feet in pursuit of giant squid, spending over an hour submerged on a single breath. Its teeth are real, dense, and built for gripping struggling prey in total darkness. Critically, the sperm whale's preferred hunting depth overlaps substantially with the Greenland shark's preferred depth range. They are in the same water at the same time, with one animal that is enormous and aggressive and built to eat large prey, and another that is enormous, slow, and toxic. Scientists examining sperm whale stomach contents have found large, unidentified shark remains on multiple occasions. Some of those remains match the body size consistent with a large Greenland shark. The remains were not always identifiable to species, leaving the question open. There is also the matter of the toxin. Sperm whales are large enough that the volume of toxic flesh from a single Greenland shark might not reach the threshold needed to cause significant neurological distress. Their digestive systems process prey differently from smaller marine mammals. Whether the antifreeze compound poses the same level of risk to a 60-foot whale as it would to a killer whale has never been directly studied. The sperm whale is the most credible candidate for Greenland shark predation, precisely because it is one of the only animals that checks every necessary box: depth range, size, predatory behaviour, and potential resistance to the toxin. But no one has ever watched it happen. Deep-sea cameras have captured extraordinary things: giant squid wrestling with sperm whales in the dark, bioluminescent creatures moving through environments that look alien. But a sperm whale actively pursuing and consuming a Greenland shark in its natural environment has never been filmed, never been directly observed, never been confirmed by any scientific account. The abyss keeps that secret. What science does know is that the interaction, if it exists, plays out in one of the least observable places on Earth. The data that would settle this question requires either extraordinary luck with existing deep-sea equipment or technology capable of sustained observation at depths where almost nothing currently operates. Until then, the sperm whale remains the leading unknown. The most likely answer to the question of what, if anything, hunts the Greenland shark, a theory built on strong circumstantial evidence and no direct proof. And that gap between what we suspect and what we can confirm opens onto something much larger about how little we actually know about the deep ocean. Humans have explored more of the moon's surface than the deep ocean floor. That fact sounds exaggerated. It is accurate. The technologies required to land a human on the moon and return them safely were developed and successfully operated decades ago. The technologies required to put a human being at the deepest points of the ocean for extended observation are harder to build, harder to maintain, and far more expensive to deploy. Less than 25% of the ocean floor has been mapped in meaningful detail. Below 3,000 feet, direct human observation is extremely rare. Continuous monitoring of any deep ocean environment, the kind needed to document a Greenland shark's actual daily life in its own habitat, essentially does not exist. What we know about the Greenland shark comes from dead animals examined on docks, from stomach contents, from satellite tags attached at the surface that transmit data when the shark rises close enough to send a signal, and from the occasional brief footage of a shark drifting past a deep sea camera lowered on a cable. Every significant fact in this story came from indirect evidence. The age estimate came from an eye lens pulled from a dead shark. The depth data came from tags that only work near the surface. The stomach contents came from sharks that were already dead when examined. The toxicity data came from animals that ate the shark and survived to display symptoms. No one has ever watched a Greenland shark hunt a live seal in its natural environment. No one has ever observed its actual social behaviour, whether it has any, at depth. No one knows how these animals find each other to reproduce. No pregnant Greenland shark has ever been observed in the wild. No Greenland shark birth has ever been documented. Scientists know they give birth to live pups, deduced from examining pregnant females caught in nets, but the actual event, where it happens, at what depth, and in what conditions, remains completely unknown. A 400-year-old animal reproducing somewhere in the Arctic abyss, in water we cannot meaningfully observe, raising offspring that will outlive every human alive today. The Greenland shark has been on Earth far longer than modern science has existed. It was old before biology was a discipline. It was ancient before anyone thought to ask questions about what lives in deep water. And yet the questions it raises keep expanding the longer scientists study it. Because the Greenland shark is not just a strange animal with extreme biology. It is a data point about how life can work under conditions that seem to exclude it. About how slow can beat fast, how deep can beat dangerous, how ancient can outlast everything that tries to remove it. Somewhere below the ice right now, moving through water no camera has filmed, older than any living human civilization has been continuously recorded, the shark keeps moving. But Orcas are not giving up on the deep ocean entirely. And what they do at the surface, the strategies they have built across thousands of years, reveals something about intelligence that changes how we think about what it means to be a predator. 2 orcas changed an entire ecosystem. Port and starboard, named for their distinctively bent dorsal fins, first appeared off the South African coast in the early 2000s. In a region where great white sharks had been a fixture for decades, drawing researchers and tourists and generating significant scientific study, these 2 orcas began hunting. Within a few years, the great whites were gone. The sharks did not fight back. They did not adapt an alternative strategy. They simply left. Scientists tracked the great whites via tags and found the animals had relocated hundreds of miles away, abandoning feeding grounds they had used for years. The orcas did not need to be everywhere. Their presence alone was enough. What port and starboard demonstrated was not just physical dominance. It was psychological dominance. Great white sharks, apex predators capable of killing almost anything in their path, experienced enough interaction with these 2 orcas to encode a fear response so strong that it overrode years of territorial behaviour. The orcas understood the liver extraction technique with surgical precision. They approached great whites, flipped them through a specific sequence of movements that induced tonic immobility, the paralysed trance state that some fish enter when inverted, and then opened the shark's body to remove the liver with minimal effort. The liver of a great white shark can weigh over 300 pounds and contains extraordinarily dense calories. For 2 orcas working as a team, a single great white provided enough energy to fuel days of activity. This specialisation did not appear overnight. It developed through years of practice and social learning within a pod. Young orcas that hunted alongside port and starboard would have observed the technique and absorbed it. If those young orcas formed their own pods later, the technique would travel with them. That is how orca knowledge spreads across the ocean. A technique mastered by 2 animals can, over generations, become standard practice across an entire region. This is exactly why the Greenland shark situation is so telling. If any orca pod in the Arctic had ever successfully hunted a Greenland shark and survived with a viable technique, that technique would exist in the cultural memory of the region by now. It would have spread. Other pods would have adopted it. Scientists tracking orca diets in the North Atlantic would eventually find evidence of it. The absence of any such technique in any Arctic orca population across all recorded history of studying these animals is evidence of something. Either no pod ever successfully attempted it, or every pod that attempted it suffered consequences severe enough to erase the knowledge entirely. Both possibilities end at the same place. The Greenland shark swims on, but there is one more layer to this. One aspect of the orca's intelligence that connects directly back to the Greenland shark and explains something about why the poison, the depth, and the cultural gap all reinforce each other in a way that makes the shark almost untouchable. Smart animals take fewer risks. This seems counterintuitive. We tend to imagine intelligence as a tool for conquering challenges, for finding ways through obstacles, for expanding what is possible, and for orcas that is true in many contexts. Their intelligence allows them to solve problems other predators cannot. Coordinate hunts, develop new techniques, adapt to changing environments. But intelligence also means better risk assessment. A less intelligent predator might charge at a Greenland shark out of hunger or aggression. It might attempt a bite and suffer the consequences. The consequences would be limited to that individual animal, and the species as a whole would not change its behaviour. An intelligent predator calculates before committing. Orcas observe before they attack. They test situations. They assess group dynamics, prey behaviour, environmental conditions, and probable outcomes before expending the enormous energy a major hunt requires. They have been observed abandoning hunts that started poorly, pulling back from prey that showed unexpected behaviour, and redirecting to easier targets when the risk-reward calculation shifted unfavourably. An orca assessing a Greenland shark from a distance sees several things simultaneously. The target is enormous, roughly the weight of a mid-sized car. It moves in an unusual way, slow and steady, generating almost no pressure waves. It lives at a depth where the orca's oxygen advantage diminishes rapidly. The environment around the target is cold, dark, and disorienting. Pursuing it requires descending below comfortable operational depth. And somewhere in the orca's cultural inheritance, there may be a residual signal, not necessarily a specific memory, but a general learned caution around this particular type of prey. Orcas show learned aversions to prey and environments that have caused problems in the past. Pods in certain regions avoid specific fishing areas where they have encountered entanglement. Pods that have seen members injured by specific prey types tend to de-emphasize that prey going forward. The cultural memory of orca pods encodes risk as clearly as it encodes reward. If any ancestral encounter with a Greenland shark went badly, that outcome would have been absorbed into the pod's general caution around this animal type. Not necessarily as a specific instruction, avoid the Greenland shark, more as a cumulative absence of positive reinforcement. The Greenland shark was never rewarded, therefore it was never pursued, therefore the skill never developed. The intelligence that makes orcas such extraordinary hunters also makes them extraordinarily good at knowing when something is not worth hunting. The Greenland shark lives inside that calculation as a permanent exception. But the story does not fully end with what orcas will not do. Because the ocean keeps changing, temperatures are rising, sea ice is retreating. The winter window that previously kept the Greenland shark protected behind ice barriers is growing longer in some areas and shifting in others. What happens when the conditions that kept these two animals separated start to change? The Arctic is warming faster than any other region on Earth. Over the past several decades, average Arctic temperatures have risen at roughly 4 times the global average rate. The sea ice that once covered enormous stretches of the Arctic Ocean year-round has shrunk dramatically. In decades past, the winter ice pack extended so far and formed so reliably that large portions of the Arctic were effectively closed to orca activity for months at a time. That is changing. As ice coverage decreases, orca populations are spending more time in the Arctic and moving deeper into regions they previously could not access. Scientists tracking North Atlantic orca movements have documented pods appearing farther north and staying longer into the cold season than historical records show. The animals are following the retreating ice edge, which means they are entering water previously dominated by the Greenland shark for much longer portions of the year. The depth barrier remains. The toxin remains. The cultural gap in hunting knowledge remains. But the seasonal ice barrier, the one factor that created a guaranteed physical separation during the window when the Greenland shark rises toward shallower water, is weakening. At the same time, warming water is affecting prey distribution throughout the North Atlantic. Fish species are shifting their ranges northward as temperatures rise. The herring and other schooling fish that North Atlantic orcapods follow are moving. The seals and small whales that marine mammal hunting orcas target are shifting their distribution as ice and ocean temperatures change. orca pods are being pushed into new territory, into environments they have less ancestral experience with, potentially encountering prey species and conditions their cultural knowledge does not fully address. Whether this brings them into more frequent contact with the Greenland shark in shallower water during the transition seasons, spring and autumn, when ice is neither fully formed nor fully gone, remains an active area of research. Some scientists watching this situation express concern. A species that has coexisted with Orcas for millennia, protected by a combination of factors that perfectly complemented each other, may be approaching a period where those factors align less reliably. The Greenland shark cannot evolve faster. Its growth rate of 1/3 of an inch per year means evolutionary change across the population takes thousands of years. It cannot suddenly develop new defences or shift its behaviour dramatically. The tools it has are the tools it has always had. The depth, the poison, the silence, the ice. If the ice continues to retreat, the calculation that has kept these two animals separated for all of recorded history may eventually be interrupted. The shark cannot change, the orca can adapt, and between those two facts sits a question that no one currently knows the answer to. For 400 years, the shark has been safe. For the next 400, the ocean it depends on is becoming something different. And what happens in the dark water beneath a warming Arctic, between the planet's oldest vertebrate and its most intelligent marine predator, may be one of the most consequential ecological stories unfolding right now in a place where almost no one can watch. 400 years old, still hunting, no cancer, no organ failure, no joints wearing down, no immune system collapsing under decades of accumulated stress. The Greenland shark carries its centuries the way a stone carries its age, without visible damage, without visible effort, simply continuing. This is not normal for large animals. Most big mammals age hard. Elephants wear through 6 sets of teeth across their lives. When the last set goes, they starve. Whales accumulate parasites, infections, and injuries that compound over decades. Great white sharks, nowhere near as long-lived as Greenland sharks, show scarring and tissue degradation that scientists can use to estimate age. The body, in most cases, keeps a record of how long it has been running. The Greenland shark's body keeps almost no such record. Biologists who study aging are increasingly interested in this animal for exactly that reason. The field of aging research looks for biological mechanisms that cause cells to deteriorate over time. One major mechanism is telomere shortening. Telomeres are protective caps on the ends of chromosomes, and each time a cell divides, the telomere gets slightly shorter. When telomeres become too short, cells stop dividing properly and begin to malfunction. This is a significant driver of aging in mammals. The Greenland shark cells divide so rarely because its metabolism runs so slowly that telomere shortening happens at a fraction of the rate seen in faster-lived animals. The slow heartbeat is not just a survival tool, it is, indirectly, a brake on the aging process itself. The shark is not immortal. Old individuals do eventually die. But the mechanisms that kill most animals, the accumulating failures of cellular machinery under the pressure of constant high-speed operation, operate in the Greenland shark at such a reduced rate that the shark essentially outruns them. Scientists studying this are drawing a direct connection between metabolic rate and lifespan across animal species. Animals with very high metabolisms, hummingbirds and shrews for instance, burn through their cellular machinery quickly and die young. Animals with very low metabolisms can sustain tissue function for extraordinary periods of time. The Greenland shark sits at the extreme end of that spectrum. The implications extend beyond sharks. If researchers can identify the specific cellular mechanisms that allow the Greenland shark to slow aging so dramatically, those mechanisms become candidates for study in human aging research. The chemistry of the antifreeze compound, the specific protein stabilization techniques the shark uses at the cellular level, the relationship between its near-zero growth rate and its resistance to cellular degradation, all of these are being actively researched. A 400-year-old shark living in the Arctic abyss might hold biological information relevant to one of the longest-running questions in human medicine. The shark, predictably, does not care. It keeps gliding through the dark at less than 1 mile per hour, hunting by smell and pressure sense, carrying its centuries without complaint. But there is one thing inside the Greenland shark's body that does carry a record of its age, not as degradation, but as information. That record sits at the centre of its eye, in proteins laid down before the shark was born, holding a signature from the moment it entered the world. And what that signature revealed about when this animal was born makes the 400-year estimate feel small. The oldest Greenland shark in the study was born around the year 1600. 1600. The year before Queen Elizabeth I died, decades before Isaac Newton was born, a century and a half before the United States existed as a concept, let alone a country. The Industrial Revolution was still 150 years away. There was no electricity, no internal combustion engine, no steel cable, no synthetic material of any kind. The ocean that shark was born into was a different world. No shipping lanes cut across the North Atlantic, no sonar pinged through the water, no propeller noise vibrated through the deep, no plastic particles drifted in the currents. The Arctic that shark first swam through was quieter, colder, and far more intact than the one it swims through today. The shark has outlived entire human empires. It was alive during the 30 Years' War in Europe. It was alive when the Pilgrims crossed the Atlantic. It was alive when the American Civil War began and ended. It was alive when the first airplane flew at Kitty Hawk. It was alive when humans landed on the moon. It is alive right now. Every significant event in modern human civilization happened within the lifespan of a single Greenland shark. Let that land for a moment. Scientists confirmed this through the radiocarbon dating process described earlier, analysing the proteins at the centre of the eye lens that form before birth and never change. The carbon signature at the core of the largest shark's lens showed ratios consistent with formation before the nuclear testing era of the 1950s and 60s, which itself confirmed a birth date of well before the 20th century. Extrapolating backward using the shark's size and known growth rate placed the birth date at roughly 4 centuries ago. There is also an important caveat the researchers themselves emphasised. The error range on that estimate is plus or minus approximately 100 years. The shark could be as young as 300 or as old as 500. The lower bound alone still makes it the oldest vertebrate ever documented. The upper bound puts its birth date in the 1500s. A fish that was already old when Shakespeare was young. The finding shocked the scientific community when it was published in the journal Science in 2016. Greenland sharks had been known to science since the 19th century. They had been caught in nets, examined on docks, analysed in laboratories. Their extreme size suggested significant age, but the actual numbers when they came in surpassed what most biologists had even theorised. No other vertebrate animal had ever been verified at these ages. Tortoises, which were previously the longevity champions among vertebrates, rarely exceeded 200 years under the best documented cases. Ocean quahog clams, invertebrates and therefore in a different biological category, have been aged past 500 years. The Greenland shark now sits between those two data points, the oldest animal with a backbone ever confirmed on Earth, and somewhere in the Arctic right now, there may be a Greenland shark alive that is older than the one they studied. The ocean is vast, the deep is mostly unsampled, the sharks avoid the surface, most of them die without ever being examined by a scientist. The record holder might still be out there. Moving slowly through the dark. Too old to have a name for what old means. Here is a question that sounds simple. What does a 400-year-old shark eat? The honest answer is almost anything that stops moving long enough. Scientists have pulled extraordinary material from Greenland shark stomachs over the decades. seals in pristine condition, captured without a struggle. Large fish. Seabirds, squid, pieces of whale carcass. And the terrestrial animals that made headlines: reindeer, polar bears, horses, and moose. Each of those finds tells a small story about opportunity. A reindeer drowned crossing a fjord during migration. A polar bear lost a battle with open water during a storm. A horse fell from a coastal cliff. A moose waded too far into a river mouth during spring flooding. Each animal that died near water, in the Arctic or subarctic, became a signal, a trail of chemical information drifting through the water column downward toward the abyss. The Greenland shark followed the trail. It does not rush. It does not need to. The carcass of a large mammal takes days or weeks to fully decompose, and the shark, arriving slowly, finds the meal still largely intact. Other scavengers in the deep ocean, hagfish and certain species of crab and deep-sea fish, also find these carcasses. But a 24-foot shark, weighing nearly 2,000 pounds, takes priority. The diversity of what shows up in these stomachs tells scientists that the Greenland shark is not a selective hunter. It is an opportunistic one. Whatever the deep ocean offers, the shark will eventually locate and consume. 400 years of this behaviour means the shark has fed through multiple cycles of ecosystem change in the Arctic, through periods when certain prey species were abundant and periods when they were scarce, through centuries of shifting prey distribution. There is something almost geological about a 400-year-old predator's relationship with its ecosystem. A human scientist studies a marine food web over a career spanning maybe 30 or 40 years. The Greenland shark has lived through 10 of those careers back to back. It has eaten prey across a time span that includes the population growth and collapse of multiple Arctic mammal species. Its stomach is less a meal record and more a 400-year archive of what the Arctic Ocean produced. This creates an unusual scientific value. If scientists could analyse the chemical composition of tissue in old Greenland sharks with enough detail, they might extract dietary information going back centuries. The ratio of certain molecules in shark tissue reflects what the animal ate, and those ratios shift as ocean chemistry and prey populations change. An old enough Greenland shark carries a chemical diary of ocean conditions, stretching back further than any human oceanographic record. The deep ocean keeps its own records. And some of the best archives are still alive, moving slowly through water that no one is watching. But while the Greenland shark's stomach holds centuries of the past, a different question about this animal points toward the future. What happens when scientists try to study something they fundamentally cannot observe? Science requires observation. To understand how an animal behaves, researchers need to see it behave. They need to watch it hunt, rest, socialize, reproduce, and navigate its environment. They need repeated observations across multiple individuals and multiple conditions. They need enough data points to distinguish pattern from accident. With the Greenland shark, almost none of this is possible. The shark lives in the abyss. Camera systems that can operate at 4,000 feet exist, but they are expensive, difficult to deploy, and can only cover a tiny area of ocean at any given time. Lowering a camera on a cable and hoping a Greenland shark passes through the frame is like placing a single motion-sensitive camera in the middle of the Amazon rainforest and hoping to document jaguar hunting behaviour. The footage that does exist is striking precisely because of how little of it there is. Scientists have brief clips of Greenland sharks near the surface, usually drawn there by bait on a research line, moving with that characteristic slow, unhurried glide. A few clips show the animals at intermediate depths near the continental slope. Almost nothing captures them in their actual preferred environment, far below any sustained human reach. Everything scientists know about the Greenland shark's reproduction comes from accidental capture. Pregnant females have been brought up in fishing nets. Examination of those females revealed the pups developing inside, giving scientists information about litter size and pup dimensions. A typical litter appears to be somewhere between 8 and 10 pups. The pups are born at around 16 inches long. But where exactly birth happens is completely unknown. At what depth the females go to give birth, what cues trigger the process, how long gestation lasts, whether males and females come together at specific locations to reproduce, whether the pups receive any parental attention after birth, whether pup mortality is high or low, none of this has been directly observed. For a species with a 400-year lifespan, these questions carry enormous weight. An animal that lives 4 centuries and reproduces slowly accumulates population changes on a timeline that makes human intervention nearly useless if the population is declining. By the time scientists detect a significant drop in Greenland shark numbers through conventional monitoring, the animals causing the decline may have been dead for decades. The Greenland shark has been caught as bycatch, an unintended victim of fishing operations in the North Atlantic for centuries. Historically, fishermen targeted it for its liver oil before petroleum products replaced it. The impact of those removals on the population is almost impossible to calculate because population estimates for this species remain extremely rough. How many Greenland sharks currently exist? Scientists can offer an informed range, but the honest answer is that no one knows. The abyss does not submit to census. An animal that old, that slow to reproduce, that difficult to observe, and that vulnerable to unmonitored removal sits in a category that conservation science has very little experience handling. The tools we have built to protect species are designed for animals we can see. For this one, we are mostly guessing at shadows. Every ecosystem has a food web. The food web describes who eats who, how energy moves from sunlight through plants, through herbivores, through predators, and how the removal of any one piece affects everything connected to it. Marine biologists have mapped food webs in most accessible ocean environments with reasonable accuracy. The deep ocean food web is different, and the Greenland shark sits somewhere inside it that no one has fully worked out. At the surface, the ocean's energy chain is relatively clear. Sunlight feeds phytoplankton. Phytoplankton feeds zooplankton. Zooplankton feeds small fish. Small fish feed larger fish. Larger fish feed marine mammals and apex predators. The energy flows upward through size. Below the sunlit zone, the food web changes character. No sunlight means no phytoplankton. Energy enters the deep ecosystem in 2 main ways. Marine snow, which is the constant slow rain of dead organic material falling from the surface, and the migrations of animals that feed at the surface at night and descend during the day. The Greenland shark feeds near the bottom of this system in terms of depth, but near the top in terms of size and energy consumption. It eats carrion from the surface world that sinks into its territory. It eats the animals that migrate through its depth range. It eats the seals and fish it can ambush. But what eats the Greenland shark? Beyond the unconfirmed sperm whale theory, the shark appears to have no regular predator. In ecological terms, this makes it a true apex predator within its zone, an animal at the top of its local food chain with no natural population check from above. Apex predators play a regulating role in ecosystems. When they are present and healthy, they suppress prey populations enough to prevent any single species from dominating. When they are removed, prey species explode in number, often with cascading effects down through the food web. The Greenland shark has been regulating the deep Arctic food web for millions of years. Its scavenging removes large carcasses from the ecosystem efficiently, cycling nutrients back into the water column. Its predation on seals and fish controls those populations at depth. Its presence and chemical signature may even influence the behaviour of other deep-sea animals that would prefer to avoid it. Remove the Greenland shark from the deep Arctic, and nothing currently known would fill its ecological role at that depth. What makes this significant is that the Greenland shark's population has faced pressure from human fishing activity for centuries, and the population-level effects of that pressure remain unmeasured. A slow-reproducing, long-lived apex predator at the top of an ecosystem we cannot see, losing individuals to bycatch at an unknown rate, represents one of the least understood conservation challenges in the ocean. We do not know how many exist. We do not know the rate at which they reproduce successfully. We do not know how the deep Arctic food web would shift if their numbers declined significantly. What we do know is that any species that has survived for 400 years, that has outlasted ice ages and ocean chemistry shifts, and the rise of every major predator currently alive, deserves more than our ignorance. The deep ocean holds a version of Earth that is older than almost anything we can observe. And somewhere in it, a living fossil is still doing its job. The Greenland shark's body plan has changed very little over millions of years. Its basic shape, the blunt snout, the small fins, the cylindrical body built for slow deep cruising, traces back to shark lineages that predate the dinosaurs. While other shark species evolved into faster, more agile forms adapted to warmer surface waters, the Greenland shark stayed in the cold and stayed slow. The deep ocean is stable. The pressure and temperature at 4,000 feet do not fluctuate the way surface conditions do. An animal adapted to stability has no evolutionary pressure to change. Scientists describe this as evolutionary conservatism. The body plan works. The environment does not change enough to penalize it. The shark does not change either, but the environment is now changing at a pace the shark has never encountered. Arctic water temperatures are rising. The chemistry of the water is shifting as more carbon dioxide dissolves into the ocean from the atmosphere, making it more acidic. The prey species the shark depends on are redistributing as temperature gradients shift. The ice that has structured Arctic ecology for millions of years is retreating at a rate that has no precedent in the geological record that covers the shark's entire evolutionary history. The Greenland shark spent 400 million years evolving for a world that is currently being dismantled in decades. Its survival toolkit is extraordinary within the context it evolved for. The depth protects it from almost every predator. The toxin provides chemical armor. The slow metabolism allows centuries of operation on minimal energy. The cold-adapted biology runs at full efficiency in conditions that would kill most other large animals. But every one of those advantages assumes a certain baseline, deep, cold, stable Arctic water with reliable ice cover and a consistent prey distribution. Warming disrupts all of it at once. Warmer water at depth, even a slight increase, alters the shark's metabolic calculations. A body tuned to operate at near freezing temperatures faces new stresses when those temperatures creep upward. The prey animals that historically sank into the shark's territory from the surface, the seals and large mammals whose populations were structured by ice ecology, are shifting their ranges and behaviours in response to ice loss. Whether the Greenland shark can adapt is a question that cannot be answered on any human timescale. An animal that grows 1/3 of an inch per year, that reproduces slowly across a lifespan of centuries, does not adapt generationally the way faster-lived animals might. Changes that evolution could compensate for in a species with short generations require thousands of years to process in a species like this. The Greenland shark faces a changing world with a biology designed for permanence. And perhaps the most remarkable thing about this animal is what it represents beyond its own survival, proof that extreme patience, extreme efficiency, and extreme depth can build something that outlasts almost everything else the planet has thrown at the ocean. The question now is whether those tools, built over hundreds of millions of years, are enough for what comes next. Orcas have been in the Arctic for a long time. They have watched the Greenland shark from a distance that science has only recently begun to measure. Their cultural knowledge, the accumulated decisions of generations of matriarchs, encodes something about this animal that researchers are still working to fully understand. The orca's avoidance of the Greenland shark is so consistent across so many ecotypes, across so many decades of observation, that it functions as a kind of peer review. The most intelligent marine predators on the planet have assessed the Greenland shark and reached a unanimous conclusion: it is not worth the attempt. That conclusion carries information. When a highly intelligent, culturally sophisticated predator consistently avoids a prey item that is large, slow, and abundant, the avoidance is a data point. It tells us something about the prey that raw biology alone does not fully capture. The orca's risk assessment, built from generations of testing and refinement, has landed on the Greenland shark as a category of problem that does not have a profitable solution. Scientists studying orca cognition describe this as niche avoidance through cultural transmission. The pod learns what works and what does not, and encodes both into the behavioral inheritance of the next generation. Successful strategies spread, failed strategies disappear. The knowledge that persists is the knowledge that kept animals alive. The Greenland shark's absence from orca diets is preserved knowledge. It is the echo of every bad outcome that reinforced the avoidance, passed forward through time until it became simply part of how the pod understands the world. Humans do not yet have access to that knowledge in any systematic way. We observe orca behavior and draw inferences. We study the shark's chemistry and physiology and draw more inferences, but the complete picture of how these two animals have coexisted, what encounters have happened, what outcomes resulted, what knowledge was encoded and why, exists entirely within the orca's cultural memory in a form we cannot directly read. This is one of the stranger aspects of studying intelligent social animals. They know things we do not. The knowledge lives in behavior rather than language, in avoidance patterns rather than explicit records, in the choices of animals who have been making those choices for far longer than human science has been watching. The orca knows something about the Greenland shark, something specific enough to produce universal avoidance, something important enough to preserve across generations. We are still working out what it is, and perhaps the most honest position science can take is that some of what we need to understand about the deep ocean will come from watching the animals that already understand it, the ones that have been navigating it for millions of years, making decisions based on information we are only beginning to access. The Greenland shark does not need us to understand it. It was here long before we were. It will likely outlast most of what we build. But there is one final dimension to this story, one that moves past the biology and the predator dynamics and the deep ocean mysteries and lands on something about time itself. Let us think about what this shark has actually lived through. 400 years ago, the Arctic was a different ocean. The waters were colder and more predictable. The ice was thicker and more permanent. The prey animals that structured the Arctic food web had never encountered industrial fishing. Whale populations across the North Atlantic were vastly larger than they are today, before commercial whaling reduced them to fractions of their historical numbers. The ocean was louder with life and quieter with machinery. Into this world, a Greenland shark was born. It did not know it. There was no ceremony. A pup approximately 16 inches long entered cold, dark water somewhere in the Arctic and began the slow process of existing. It ate small things. It grew at 1/3 of an inch per year. It descended toward depth as it grew larger. The decades accumulated. While it grew, the world above the surface changed with a speed that has no parallel in the planet's recent history. Human populations exploded. Forests were cut across continents. Rivers were dammed and redirected. The atmosphere changed its chemical composition. The ocean's temperature began a slow climb. Species went extinct at rates that fossil records suggest have not occurred since the mass extinction events that ended entire geological eras. The shark kept swimming. It did not adapt to these changes in any observable way. It could not. Its biology is not built for rapid adaptation. But it did not need to adapt. The deep Arctic, for most of those 400 years, changed slowly enough that the shark's ancient toolkit remained sufficient. The poison still worked. The depth still protected. The cold still sustained the metabolism. The ice still sealed off the winter shallows. What this animal represents is a kind of biological staying power that has almost no equivalent in the modern world. A body plan tested against 400 million years of changing conditions, refined by the coldest and most unforgiving environment on the planet, running at the minimum energy setting while everything faster around it burns out and disappears. The great white shark, often called the ocean's most iconic predator, lives perhaps 70 years. The orca, the ocean's most intelligent predator, lives perhaps 90 years in the wild. The Greenland shark looks at both of those timescales the way a mountain looks at a season. There is a version of success that does not look like dominance. The orca dominates. It is fast, smart, social, and feared across every ocean. The Greenland shark does none of those things. It is slow, solitary, nearly blind, and actively avoided as a food source. But in the race between the orca's brilliance and the shark's patience, the shark has been winning for longer than human civilization has existed. And what comes next, the question of what ultimately decides the shark's future, belongs not to the orca and not to the deep ocean, but to the only predator the Greenland shark has never evolved a defense against. Every defense the Greenland shark has ever needed evolved in response to something in the ocean. The depth protects it from air-breathing predators. The toxin protects it from anything that tries to eat it. The slow movement keeps it invisible to echolocation. The cold biology keeps it alive in an environment most animals cannot survive. Each layer of protection is a response to a real threat that existed in the shark's evolutionary history. None of those defenses work against us. The Greenland shark was first commercially targeted in the 19th century, primarily for its liver oil. Before petroleum products became widely available, shark liver oil served as an industrial lubricant and fuel source. The Greenland shark, with its enormous liver sometimes making up a quarter of its total body weight, was an attractive target. Fishermen in Iceland, Greenland, and Norway harvested these sharks in significant numbers across the late 1800s and early 1900s. The shark had no behavioural response. It did not school up for defence. It did not change its depth range. It did not increase its reproduction rate. It simply continued doing what it had always done, and the fishing continued until the market for shark liver oil collapsed following the rise of petroleum-based alternatives. No one measured the population impact of that harvesting period. By the time scientists began paying serious attention to Greenland shark population dynamics, the industrial harvest was over and decades had passed. The animals that were removed during that period, if they were adults, might have been hundreds of years old. Their absence from the breeding population could ripple forward across centuries, because a species that reproduces this slowly does not bounce back on any human timescale. Today, the Greenland shark continues to die as bycatch. Fishing operations targeting halibut, Greenland turbot, and other commercially valuable species in the North Atlantic and Arctic frequently catch Greenland sharks in their nets and on their lines. Many of these catches are not reported. The sharks are often discarded. The exact scale of bycatch mortality remains poorly documented. The International Union for Conservation of Nature lists the Greenland shark as vulnerable to extinction, the same category as the hippopotamus and the polar bear. That designation reflects the combination of slow reproduction, evidence of historical overharvesting, ongoing bycatch pressure, and deep uncertainty about current population size. A vulnerable species, an animal that may be 400 years old, a population we cannot count, in a habitat we cannot monitor, subject to pressures we cannot fully quantify. The Greenland shark survived the orca. It survived the sperm whale. It survived every apex predator the ocean produced across 400 million years of evolution. The threat it was never designed for arrived in the last 200 years with nets and engines and industrial efficiency. And the tragedy is that the shark cannot even detect it coming. The fishing line drops from a world the shark has never evolved to sense. There is no chemical warning, no pressure wave from a predator, no behavioural cue, just the hook. And then the surface. A Greenland shark on the surface is a different animal from the one in the abyss. Brought up from depth too quickly, the shark cannot regulate the pressure change through its body. Its tissues, adapted for crushing deep water pressure, find themselves in an environment where that pressure is gone. The animal is often disoriented, moving slowly even by its own standards, unable to dive back down immediately. For centuries, this vulnerability made the shark easy to catch. Historical accounts from Greenlandic and Icelandic fishermen describe using lines baited with large chunks of meat dropped to significant depth, hauled up over hours. The shark, moving slowly and investigating the scent, would take the bait and be pulled to the surface with minimal resistance. Its own biology worked against it in this context. The slow metabolism meant no explosive burst of speed to break free. The cold temperature meant reduced muscle reactivity. The shark arrived at the surface already compromised. Greenlandic Inuit communities historically used almost every part of the shark they caught. The skin, tough and rough textured, served as non-slip material for boot soles. The teeth were used as tools. The liver oil had practical applications. The flesh, after months of fermentation, became a food source in environments where alternatives were scarce. This relationship between human communities and the Greenland shark stretched back centuries, possibly longer. The Inuit were not operating on an industrial scale. Their harvesting, while consistent, likely did not approach the volumes that would significantly affect a population operating across the entire North Atlantic and Arctic. The industrial fishery was different in scale by an enormous factor. Modern fishing vessels do not wait for sharks. They deploy long lines stretching miles through the water column, studded with hundreds of baited hooks at intervals. Any slow-moving, scavenging animal in the vicinity will eventually encounter the bait. The Greenland shark's greatest survival advantage, its willingness to approach almost any food source in its territory, becomes a fatal vulnerability against this technology. The shark smells the bait, approaches, takes it, and finds itself connected to something it has no context for. Once caught and brought to the surface, most Greenland sharks that end up as bycatch do not survive release even when fishermen attempt it. The pressure change causes internal damage. The animal's cold metabolism does not recover quickly from the stress. Released sharks often show visible signs of distress and may not make it back to depth. Each lost Greenland shark, depending on its age, represents not just one animal, but potentially centuries of future reproduction removed from the gene pool. An animal killed at age 200 has, under normal circumstances, 200 more years of potential breeding ahead of it. That is not how we usually think about fisheries management. Our models are built around species that live decades, not centuries. The Greenland shark requires a completely different framework, one that most fisheries management systems are not currently equipped to provide. The ocean has kept this animal alive for 400 million years. Keeping it alive for the next century may be entirely up to us. Everything the Greenland shark does looks like a disadvantage until you look at the timescale. Slow, over 400 years. Slow means you never burn out. Nearly blind? At 4,000 feet in total darkness, sight was never the primary tool. Toxic flesh? Every predator in the region has learned, one way or another, to leave you alone. Low metabolism? Every calorie you consume lasts longer than it would in any faster animal. Reproduce infrequently? In a stable environment, keeping numbers steady across centuries requires far less reproductive effort than racing to replace fast-dying individuals. Every single trait that seems like a weakness is a long-term strategy. The Greenland shark is not poorly designed. It is designed for a different game than most animals play. Most species compete on speed, aggression, reproduction rate, or adaptability. The Greenland shark competes on time. It outlasts. It outwears. It outlives. This is a survival strategy that works spectacularly under one condition: the environment must stay stable long enough for patience to pay off. The deep Arctic Ocean was that environment for hundreds of millions of years. Cold, dark, consistent, and deep enough to insulate the shark from almost every surface world change. The extinction events that ended the dinosaurs, the glacial cycles that buried continents under ice, the ocean chemistry shifts that killed off entire marine ecosystems. The Greenland shark's preferred habitat in the deep cold north remained relatively stable through all of it. The shark survived not by being tough enough to fight change, but by living somewhere that did not change. That is a profound lesson in a different kind of strength. Speed and aggression win in volatile environments. Patience and depth win in stable ones. The orca chose the volatile path, fast, adaptable, culturally dynamic, quick to update its strategies as conditions changed. The Greenland shark chose the stable path, slow, unchanging, deeply specialized, betting everything on the consistency of the deep ocean. Both strategies produced apex predators. One of them is 400 years old. Whether the lesson scales to the current moment is the real question. The deep ocean, the source of the Greenland shark's stability advantage, is itself becoming less stable. The warming, the acidification, the shifting currents and changing prey distributions, these are not surface problems that the depth insulates the shark from. They are whole ocean problems that reach into the abyss. The shark's strategy has never been tested against this specific kind of change. Geological records show that ocean chemistry shifts on timescales of millions of years happened before, and the Greenland shark's lineage survived them. But those shifts unfolded over timescales long enough for even slow evolutionary processes to respond. What is happening now is faster. The question of whether the Greenland shark's ancient playbook is sufficient for a new kind of ocean is one that no scientist currently alive will see answered. The answer will be written in the deep water over the next several centuries, and the shark will be writing at 1/3 of an inch at a time. The Greenland shark is actively changing what scientists think is possible. Before the 2016 study confirmed 400-year lifespans, the scientific consensus placed the upper limit for vertebrate lifespan well below that. Tortoises were the benchmark. Bowhead whales, some of which have been found with 19th century harpoon tips embedded in their tissue, suggested lifespans approaching 200 years. The Greenland shark doubled the known upper limit. That kind of revision does not happen often in biology. When a single data point forces a rewrite of what the field thought it understood about the boundaries of life, it signals something important. There are likely other discoveries still waiting in underexplored environments that will require similar revisions. The deep ocean is the largest underexplored environment on Earth. It covers more area than all the continents combined. Its extreme conditions, crushing pressure, near freezing temperatures, total darkness, have historically made sustained scientific observation nearly impossible with available technology. The animals living there have largely been discovered by accident, pulled up in nets, found dead on beaches, glimpsed briefly by remotely operated deep-sea cameras lowered on cables. The active scientific understanding of deep-sea ecosystems is built on a tiny fraction of available data. The Greenland shark's confirmation as the world's oldest vertebrate opened a new set of questions that researchers are now actively pursuing. What cellular mechanisms allow such extreme longevity in cold water? Can those mechanisms be replicated or stimulated in other biological contexts, including human tissue? What does the shark's extraordinary resistance to cell degradation tell us about the relationship between metabolic rate and biological aging? Several research teams around the world are now studying Greenland shark tissue specifically for aging-related biological information. The antifreeze compound itself, trimethylamine oxide, is being examined not just as a toxin, but as a protein stabilizer, something that could have applications in fields ranging from medicine to food preservation. The same chemistry that protects the shark's cells from freezing damage may offer insights into how proteins can be stabilized under extreme conditions, with potential applications in pharmaceutical storage, organ transplant logistics, and the study of age-related diseases in humans. A 400-year-old shark living in the dark at the bottom of the Arctic is, unexpectedly, a contributor to human medical research, and almost none of it would have been discovered without the combination of a fishing net pulling one to the surface and a scientist wondering exactly how old it was. The ocean has more of these moments waiting, more data points that will require scientists to revise what they thought was possible, more ancient things moving through the dark that no one has yet thought to look for in the right way. The Greenland shark will not survive to see what those discoveries are, but it will still be swimming when we make them. If a 400-year-old shark can exist in the deep ocean without anyone knowing how old it was for most of recorded history, what else is down there? The question is not rhetorical. Deep-sea biology has repeatedly surprised researchers with the discovery of animals either previously unknown or known only from fossil records and assumed to be extinct. The coelacanth, a fish whose body plan dates back 350 million years, was believed extinct until a live specimen was found in a fishing net off South Africa in 1938. The megamouth shark, a large filter-feeding shark reaching 17 feet in length, was entirely unknown to science until 1976, when one was accidentally pulled up by a naval research vessel anchoring at depth. These were not small discoveries. These were large animals living in accessible areas of the ocean that had been fished and studied for centuries. What lives at 4,000 feet in waters that see almost no human activity is a different question entirely. Sperm whale stomach contents have yielded remains of giant squid that, when reconstructed from suckers and beaks, suggest body sizes beyond anything ever directly observed. One estimate from recovered tissue placed a tentacle span at potentially over 40 feet. The largest verified giant squid ever directly measured reached about 43 feet in total length, but the evidence from whale stomachs suggests the upper limit of squid size may be larger than the confirmed record. Deep-sea cameras baited with fish carcasses and lowered to extreme depths in the Pacific have returned footage of amphipod crustaceans, organisms related to the shrimp that live in tide pools reaching lengths of almost a foot. The same family of animal, on the surface, tops out at about an inch. Deep-sea gigantism, the phenomenon where certain invertebrates grow far larger at extreme depths, suggests that body size rules in the deep ocean do not follow the same constraints as at the surface. The Greenland shark may not be the only organism at extreme depth that has been operating on a radically different biological timescale than anything we have studied. There could be other deep-sea vertebrates with lifespans approaching or exceeding the Greenland shark. There could be deep-sea invertebrates with lifespans stretching past any currently confirmed record. The biology of extreme depth is consistent with very long life. Low temperatures slow every metabolic process, reducing cell degradation and extending viable lifespan in principle. We simply do not know. We have not looked long enough or deep enough. What we do know is that the discovery of the Greenland shark's age changed the conversation about what biological time looks like in the deep ocean, and changed conversations in science tend to lead to more discoveries. The deep is not empty, it is full of things we have not yet understood. For centuries, the Greenland shark and the Inuit communities of the Arctic shared the same cold territory. This coexistence produced something unusual, a human culture that understood the Greenland shark's nature and responded to it practically, without the tools of modern science. Inuit hunters knew the shark's flesh was dangerous. They knew through generations of experience that dogs fed raw shark became incapacitated. They knew the fermentation process required to render the meat safe. They knew where the sharks could be found, at what depths, in what seasons. They knew the liver's properties and uses. They encoded all of this into practical knowledge that sustained communities in one of the harshest environments humans have ever inhabited. This is not romantic, it is functional. The Inuit did not revere the Greenland shark or fear it as a mythological creature. They understood it as a resource with specific properties and specific risks, and they developed the techniques needed to extract value from it safely. That knowledge took centuries to develop and represents a form of ecological understanding that parallels what marine biologists are only now formalizing with scientific tools. The traditional ecological knowledge of Arctic communities about the Greenland shark is increasingly being recognized by researchers as a legitimate data source. Indigenous hunters who have observed shark behavior over lifetimes in waters they have fished for generations sometimes hold observational data about where the sharks appear when they approach the surface, what they seem to react to, that no scientist has formally recorded. One researcher working in Greenland described interviewing an elder hunter who had decades of personal experience pulling Greenland sharks from specific locations at specific times of year. The patterns the Elder described match satellite tagging data gathered with modern equipment, but predated that technology by generations. The deep ocean is difficult for science to observe. The communities that have lived beside it longest have been watching for far longer than research vessels have been running their instruments. That combination, traditional knowledge informing and validating scientific data, represents one of the more underused resources in understanding animals like the Greenland shark. The shark has been part of human ecological understanding for centuries. The scientific community is still catching up to what Arctic communities have known for a long time. There is a moment in every deep-sea research expedition where the tools run out, the camera reaches its depth limit, the cable runs to its end, the remotely operated vehicle's battery drops, the time window closes, the ship must return to port. And in the water below, in the dark that no instrument currently operating can reach continuously, the lives of the animals down there proceed exactly as they always have. For the Greenland shark, that unreachable zone is home. The questions that matter most about this animal, the ones that would tell us whether it is thriving or quietly declining, whether its population is stable or contracting, whether the changing Arctic is already affecting it, or whether the deep provides enough insulation to delay the impact, all of those questions live in a space we cannot currently access with the tools we have. How many Greenland sharks exist right now? Scientists estimate the population across the North Atlantic and Arctic in the tens of thousands, possibly more. But that estimate is built on indirect evidence, the rate at which they appear in bycatch, the surface area of their habitat, the estimated prey availability in their range, and the very rough understanding of their reproductive rate. It is a guess built on other guesses, an honest one, but a guess. Whether the population is stable requires data over time, ideally from direct observation of a representative sample across multiple decades. The data that exists is fragmentary, drawn from accidental encounters, short-term tagging studies, and the limited footage available from deep-sea cameras. This is not a failure of science. It is a genuine limit of what current technology can observe in an extreme environment. What would be needed to meaningfully monitor the Greenland shark population would be something like a network of long-term deep-sea monitoring stations in the shark's core habitat range, capable of sustained observation over years rather than hours. Camera systems robust enough to operate at 4,000 feet continuously, for long enough to build a statistically meaningful picture of how many sharks pass through a given area at a given time. That infrastructure does not currently exist. Building it would be enormously expensive and technically challenging. Whether the scientific and policy community will prioritize it before the population data becomes truly urgent is an open question. The Greenland shark has survived without human attention for 400 million years. It does not need us to observe it in order to continue existing, provided the conditions it evolved for remain sufficiently intact. What monitoring would provide is early warning, a signal early enough that protective measures could be implemented before population decline becomes irreversible on the timescale of a species that reproduces as slowly as this one does. Once the signal becomes obvious without sophisticated monitoring, it may already be too late to act on it in any meaningful way within a human lifetime. That is the specific, uncomfortable nature of the conservation challenge the Greenland shark represents. The Greenland shark was here before history. It was here before the first written language, before the first city, before the first ocean-going vessel, before any human concept of the ocean as something to be navigated, fished or studied. When the first people arrived in the Arctic and looked out at the cold water, the Greenland shark was already ancient. 400 years is the confirmed age of the oldest individual studied. The species itself, the lineage that produced the Greenland shark, stretches back in the fossil record hundreds of millions of years. Individual sharks living today may carry 4 centuries of memory in their tissues. The species as a whole carries 400 million years of evolutionary information in its genome. This is a deep-time animal. a creature built not for any particular moment, but for the long, unbroken continuity of cold, dark water. And the ocean it is swimming into now is one its biology has never encountered before. The Arctic is warming, the ice is retreating, the prey is shifting, the water chemistry is changing. The orca populations are expanding northward. The fishing pressure continues, the monitoring remains inadequate. Against all of that, the Greenland shark brings the same tools it has always brought: patience, depth, poison, and time. Whether those tools are enough for this specific moment in the planet's history is a question that will unfold over centuries. The shark will not know the answer in any way a human mind can understand. It will simply keep swimming. 1/3 of an inch of growth per year. 1 heartbeat every 12 seconds. 4,000 feet below the surface, moving through the dark at less than 1 mile per hour. The orca, for all its brilliance, cannot follow it there. No predator in the ocean's history has successfully made the Greenland shark a regular meal. The depth holds. The poison holds. The cold holds. What may finally change the outcome is something that operates on a completely different level than predator and prey: the transformation of the ocean itself. An environment becoming something new, on a timescale that has no precedent in the shark's evolutionary memory. The Greenland shark does not know any of this. It does not need to. It is doing what it has always done. And somewhere beneath the ice right now, in water that no camera is watching and no instrument is measuring, a 400-year-old animal is continuing a life that started before your country existed. Still slow. Still deep. Still alive. If you made it this far, leave a like and subscribe. There is more waiting in the deep, and we are just getting started.